Welcome to Compact Disasters from compacthistories.com, where we look at catastrophes, accidents, and natural disasters in short, bite-sized episodes. This is episode 91, the Laki Fissure Eruption. Iceland lies across the mid-Atlantic ridge, where the North American tectonic plate and the Eurasian tectonic plate are slowly moving apart. Magma rises to fill the space created by this movement, making the island one of the most volcanically active regions in the world. Iceland is also positioned above an area of unusually hot mantle, often described as a mantle plume. The combination of plate separation and this additional heat produces frequent earthquakes, eruptions, and geothermal activity. The Laki fissure belongs to the Grímsvötn volcanic system in southern Iceland. Grímsvötn is a central volcano beneath the Vatnajökull ice cap, but its system also includes a long fissure swarm extending beyond the glacier. Magma can move sideways from the central region and force open cracks many kilometers away. The 1783 eruption occurred along one of these cracks, southwest of Grímsvötn, rather than from the summit of a conventional volcanic cone. The name Laki properly refers to a mountain crossed by the eruptive fissure. The resulting line of craters is known in Icelandic as Lakagigar, meaning the craters of Laki. The crater row runs approximately northeast to southwest and is about 27 kilometers long. It lies between Vatnajökull and Mýrdalsjökull, in an area where earlier eruptions had already produced extensive lava fields. In the 18th century, southern Iceland was sparsely populated. Most families depended on livestock farming, particularly sheep and cattle, supplemented by fishing where coastal access allowed it. Hay had to be gathered during the short summer and stored to feed animals through winter. This system left communities vulnerable to any event that damaged grass, killed livestock, or interrupted food supplies. Denmark then governed Iceland, and overseas trade was controlled through authorized trading posts. There was no scientific monitoring network capable of detecting rising magma. Information about the eruption therefore comes from physical deposits, later geological research, and contemporary witnesses. The most important local account was written by Jon Steingrimsson, a Lutheran priest based near Kirkjubæjarklaustur. His record described earthquakes, ash, gas, damage to farmland, and the deteriorating health of animals and people. Earthquakes were felt in the region before the eruption, indicating that magma was moving underground and breaking through the crust. The volcanic system had the capacity to produce both explosive activity and large volumes of basaltic lava. When the fissure opened, the effects would not remain confined to the immediate area. The event developed into one of the largest basaltic eruptions documented during the historical period. The eruption began on the 8th of June 1783, which was Whit Sunday. The first activity occurred southwest of the main Grímsvötn volcano after a period of earthquakes. Magma reached the surface along a newly opened fissure and encountered groundwater. This interaction produced violent explosions that broke the magma and surrounding rock into fragments, sending columns of ash and gas into the atmosphere. The eruption did not begin simultaneously along the entire crater row. Activity moved progressively along the fissure as magma forced open new sections. Each new episode was generally preceded by earthquakes. It then began with an explosive phase lasting from several hours to several days, followed by sustained lava fountaining and lava discharge. Geological reconstruction indicates that 10 main eruptive episodes occurred during the first 5 months. The initial eruption rate was extremely high. During the first 12 days, approximately 6 cubic kilometers of magma were released as lava and tephra. This represented about 40% of the eruption's eventual total. estimates of the peak discharge rate range from 5,000 to 6,600 cubic meters of magma per second. The first weeks, therefore, produced a large proportion of both the lava and the volcanic gases associated with the disaster. Lava entered the valleys of the Skafta and Haverfisfljót rivers. Water trapped beneath or in front of the flows produced steam explosions, while the lava followed river channels towards inhabited districts. Farms were destroyed or abandoned, although the lava did not directly kill large numbers of people. Residents had enough warning to move away from advancing flows, which travelled more slowly once they spread across flatter ground. Kirkjubæjarklaustur was among the communities threatened. On the 20th of July, Jón Steingrímsson conducted a church service while lava was advancing in the area. Later tradition called this the fire mass because the flow stopped before reaching the settlement. The service did take place, but geological features and the behavior of the lava provide the physical explanation for where the flow halted. Steingrímsson's importance rests primarily on his detailed observations and his work supporting the local population. The eruption also produced ashfall, sulphurous smells, and a persistent haze. Residents reported irritation of the eyes, skin, and throat, as well as difficulty breathing. These effects showed that the danger extended beyond the lava itself. As new vents continued to open, the event changed from a local lava emergency into a prolonged environmental crisis. The scale of that crisis became clearer as the fissure continued erupting through the summer and autumn of 1783. The Laki eruption continued from the 8th of June 1783 until the 7th of February 1784. Its most intense phase occurred during the first 6 weeks, followed by a gradual reduction in activity. Approximately 60% of the magma had erupted by the end of July, and about 93% had emerged by the end of the 10th eruptive episode in October. Lava and gas continued to escape during the winter, but at a much lower rate. More than 100 vents formed along the fissure, creating the crater row now called Laki. Some vents produced ash-rich explosive columns, while others generated sustained lava fountains. The eruption columns reached heights of at least 9 kilometers during the early stages. Most of the magma was basalt, a relatively fluid type of molten rock capable of traveling considerable distances when supplied at a high rate. The eruption produced an estimated 14.7 cubic kilometers of lava. The resulting flows covered roughly 565 square kilometers, filling river gorges and spreading across lowland areas. There were both smooth, ropey pahoho flows and rougher lava. The eruption also produced about 0.4 cubic kilometers of tephra, measured as compacted material. By volume, however, lava was the dominant product. The quantity of volcanic gas made Laki particularly destructive. Scientific estimates indicate that it released approximately 122 million tons of sulfur dioxide. Around 95 million tons reached the upper troposphere and lower stratosphere, where winds could transport it far beyond Iceland. Much of the sulfur dioxide reacted with water in the atmosphere to form sulfuric acid aerosols. The repeated eruptive episodes continually added more material to the developing haze. Laki also released fluoride compounds. Estimates suggest that about 8 million tons of fluoride were emitted, although not all of it was deposited in the same place or at the same concentration. Close to the eruption, fluoride attached to fine ash and contaminated grass and water. This created a serious hazard for grazing livestock because animals consumed the contaminated vegetation repeatedly. The physical size of the lava field established Laki as one of the largest basaltic eruptions of the historical period. However, The lava was not the main cause of death. No substantial number of people is known to have been killed directly by lava, explosions or ashfall. The greater damage developed through contamination of farmland, destruction of livestock, and interruption of the food supply. The haze and hardship following the eruption became known in Iceland as the Modohardindin, usually translated as the mist hardships. Ash and chemical deposits settled on pastures across the country. Acid precipitation damaged vegetation, while fluoride contaminated grass eaten by sheep, cattle and horses. These effects reached districts far beyond the lava field and continued after the most active phase of the eruption had ended. Livestock developed acute and chronic fluoride poisoning. Contemporary descriptions included loss of appetite, weakness, damaged teeth, swollen joints, and abnormal bone growth. Animals could no longer graze or move normally, and many died. National estimates vary, but approximately 3/4 of Iceland's sheep and around half of its cattle and horses were lost. Milk production also fell sharply. These losses removed the main sources of meat, milk, wool, transport, and stored wealth available to farming families. Hay crops had also been damaged, leaving fewer supplies for surviving animals during winter. People slaughtered some livestock before it died, but this provided only temporary relief. Inland districts with limited access to fishing were particularly exposed because they had few alternative sources of food. The resulting famine developed during 1784 and 1785. Malnutrition weakened the population and made people more vulnerable to infectious diseases. Some families left their farms and moved towards coastal districts, where fishing and imported supplies offered a better chance of survival. Migration placed additional pressure on those communities and contributed to overcrowding and the transmission of disease. Relief from the Danish authorities was limited and slow. Food available through Danish trading posts varied considerably between regions. Government-supported supplies arriving from the summer of 1784 amounted to only about 2 weeks of provisions when calculated across the entire Icelandic population. Some refugees and farmers near the eruption received financial assistance, but aid could not replace the livestock and agricultural production that had been lost. Iceland's recorded population fell from 49,609 at the beginning of 1783 to 40,381 at the beginning of 1786. This decline reflected excess deaths as well as a reduction in births. Recent analysis estimates excess mortality during 1784 and 1785 at approximately 8,000 people, or about 1/6 of the pre-crisis population. Older accounts often give a figure closer to 1/5. Research using parish registers supports hunger and disease as the principal causes of death. Although fluoride clearly poisoned livestock, evidence for widespread fatal fluorosis among humans is weak. Direct deaths from volcanic air pollution are also difficult to demonstrate from Icelandic records. The main human disaster arose through the collapse of the food system. A 2024 study of Icelandic mortality found that regional patterns of hunger, disease, fishing access, and food aid explain the recorded deaths more convincingly than direct poisoning. Most of Laki's sulfur emissions were carried away from Iceland at high altitude. Sulfur dioxide reacted with atmospheric moisture to form sulfate and sulfuric acid aerosols. Winds then transported this material across the North Atlantic and Europe. High-pressure weather systems caused some of the polluted air to descend towards the ground, producing the persistent haze described by contemporary observers as a dry fog. The haze was reported in several parts of Europe within days of the eruption. It reached Prague by the 16th of June, parts of Italy and Switzerland around the 17th and 18th of June, and France shortly afterwards. Observers in England recorded it on the 22nd and 23rd of June. Reports eventually came from a much wider area, including Scandinavia, Russia, North Africa, and Western Asia. Unlike an ordinary fog, it did not require damp or still conditions. It remained when the wind changed and was sometimes unaffected by rain. The sun appeared pale or red, visibility declined, and a sulphurous smell was noticed in some locations. Reports also described irritated eyes, sore throats, headaches, and breathing difficulties. People with existing respiratory illnesses were likely to have been especially vulnerable. Vegetation was damaged in parts of Europe. Leaves became discolored or fell from trees, and some crops withered after exposure to the polluted air. However, historical evidence does not support claims of a general European harvest failure caused by Laki in 1783. Local agricultural damage occurred, but crop yields were influenced by weather, soil conditions, and farming practices, as well as volcanic pollution. Several studies have identified elevated mortality in England and France during the late summer of 1783 and the following winter. One estimate calculated approximately 11,500 excess deaths in England during August and September, followed by another 8,200 in January and February. These deaths have often been attributed directly to Laki's air pollution, but the relationship is disputed. The strongest haze arrived weeks before the main increase in mortality, whereas severe modern pollution events generally produce a rapid rise in illness and death. Contagious disease, heat, and the severe winter may account for a substantial part of the mortality. Current evidence confirms that the haze caused respiratory symptoms, but it does not establish that pollution alone killed tens of thousands of Europeans. People initially struggled to identify the source. French naturalist Mourgue de Montredon connected the haze with volcanic activity in Iceland in August 1783. Benjamin Franklin later made a similar proposal. These observations helped establish that volcanic gases could cross national borders and influence atmospheric conditions far from their source. Europe experienced unusual weather during and after the Laki eruption. The summer of 1783 was exceptionally warm in many western areas, while the winter of 1783 to 1784 was extremely cold in both Europe and parts of North America. Rivers froze, snow remained for prolonged periods, and spring thaws contributed to flooding. These events occurred while volcanic aerosols were present in the atmosphere. Benjamin Franklin suggested that the Icelandic haze had reduced the amount of sunlight reaching the ground and contributed to the cold winter. Modern climate models support the conclusion that Laki could have produced winter cooling, particularly by affecting atmospheric circulation at northern latitudes. However, the relationship between one eruption and weather in a specific location is not simple. Recent modelling indicates that Laki did not cause the hot European summer of 1783. That heat was mainly the result of natural weather variability, and might have been even stronger without the aerosols. The eruption probably contributed to subsequent cooling, but researchers continue to debate how much of the severe winter can be assigned to Laki rather than existing circulation patterns. Claims that the eruption directly caused the French Revolution are also unsupported. France experienced poor harvests, high food prices, and social instability during the 1780s, but the revolution began 6 years after the eruption. Laki may have contributed to a period of climatic and agricultural pressure, but political inequality, government debt, taxation, and repeated harvest problems were much more direct causes. It should therefore be treated as one possible environmental influence, not as an explanation for the revolution. In Iceland, recovery took years. Farms had to be resettled, livestock populations rebuilt, and damaged grazing land restored. Some migration towards fishing districts became permanent. The disaster also exposed the weaknesses of Iceland's food distribution and the limited relief available under Danish administration. Jon Stangrimsson's written account preserved detailed information that later helped historians and volcanologists reconstruct the event. Laki is now protected within Vatnajökull National Park. The crater row and lava fields remain visible, providing direct evidence of the eruption's scale. Scientists study Laki to understand the hazards posed by long-lasting fissure eruptions, particularly the release of sulfur dioxide rather than ash alone. Modern monitoring would detect earthquakes, ground deformation, and gas emissions before or during a similar event. Even so, a Laki-scale eruption would create major problems for agriculture, public health, aviation, and transport across the Northern Hemisphere. Its main lesson is that an eruption does not need to produce a towering central volcano or large numbers of direct casualties to become an international disaster. That brings us to the end of this episode of Compact Disasters, part of the Compact Histories Network. If you enjoyed it, please follow or subscribe wherever you're listening so you don't miss any future episodes. And consider leaving a rating or review, as it really helps new listeners find the show. You can find more episodes at compactdisasters.com, where you can also explore our other podcasts covering biographies, history, true crime, warfare, and mysteries. You can also follow us on Facebook, Instagram, and Pinterest. Finally, please consider supporting the show directly by buying us a coffee. Head on over to compacthistories.com/disasterscoffee to see how. Thanks for listening, and I'll see you next time.